Good evening. We're going to be looking at this evening at optimization, which is just another word for finding absolute maxes and mins. You already know the process for finding absolute maxes and mins. At least one process that we've done so far has been to find critical points and then to evaluate a function at its critical points and endpoints. The largest of these is the absolute max. The smallest of these is the absolute min. So we're going to be using that process for these problems that we're going to work tonight. However, these problems are going to be given to us in terms of verbal descriptions. So a large part of what we're going to focus on is translating directly from English into math. So as we do these optimization problems, I want you to pay attention to that process of how we get from English into math. In particular, we're going to be looking at three problems from your book. If you have your book, get it out and turn to page 226. We're going to be looking at problem number 1, followed by problem number 15, followed by problem number 5. In problem number 1, we are told that the sum of two non-negative numbers is 20. Find the numbers if the sum of their squares is as large as possible, as small as possible. One number plus the square root of the other is as large as possible, as small as possible. Technically, these are 4 different problems. However, as we use the critical points and endpoints method, we're going to end up solving 2 problems at once. And as a result, really, we're just looking at 2 problems here, problem A and problem B. So let's start at the top. Our first sentence is, the sum of 2 non-negative numbers is 20. Now, I don't know these numbers, and so I'm going to solve that problem by calling them something, x and y. And the sum of those 2 numbers is x plus y, and we are told that that sum is 20. So the English sentence translates into a math sentence right here. What about the non-negative part? Well, the non-negative part is going to set a domain for us. Because my numbers are non-negative, that means that they must be greater than or equal to 0. Now, as soon as we see this, we wonder, is there a largest possible value for x? And by thinking about it for just a minute, you can see that x cannot be larger than 20, because if x is larger than 20, then y would have to be less than 0. Therefore, we have an upper bound for x and for y as well. Let's do that symbol a little bit more accurately. There we go. So now we have a domain, and we also have a statement that the sum of my 2 numbers is equal to 20. Now we're supposed to find those numbers if the sum of their squares is as large as possible. As large as possible is a key word that means maximum. We're looking for the absolute maximum. What are we looking for the absolute maximum of? We're looking for the absolute maximum of the sum of their squares. So we need to construct the sum of their squares, which is going to be x squared plus y squared. And because that sum of squares is a function, we're going to call it some kind of function. Let's call it s, or sum. Notice that in 2 different places, we have created variables out of thin air to represent unknowns that we did not know. And that's really the key to this. To be successful at this, you have to be willing to say, I don't know what this is, let me call it a variable. And we're going to call the sum of their squares s. We want the sum of the squares to be as large as possible. In a separate problem, we want the sum of the squares to be as small as possible. And that's the key word that means absolute minimum. And because our critical points and endpoints method finds the absolute maximum and the absolute minimum together, we can really solve both of these problems together. What we are trying to find the max for and the min for is this function, s. And we know something about x and y. We know that x and y are constrained by the fact that x plus y has to equal 20. And that fact allows us to substitute for either x or for y in our function. Here I'm going to substitute for y. Y is equal to 20 minus x. And I can substitute, therefore, directly for y here to find out that s is equal to x squared plus 20 minus x, quantity squared. This substitution was crucial because I'm about to take a derivative of s in order to find the critical points. And you cannot, at this point, take the derivative of a function of more than one variable. That will change far in the future when you take Calc 3. But for now, we can only take the derivatives of functions of one variable. So it was necessary that I substitute away either the y or the x in order to get a function of one variable. By the way, if I substituted for x instead, then I would have gotten this result. I would have gotten s is equal to 20 minus y squared plus y squared. Both of these equations can be used to solve the problem. I'm going to choose the one in blue. Okay, so how do we do this? Well, at this point, we're in familiar territory. We are trying to find the maximum of our function s, and so we fall into the process that you're familiar with. Critical points, and then critical points and endpoints. Let me give myself a little bit of room to work by increasing the space here. And so we have our function s equals x squared plus 20 minus x squared, and so we're ready for a derivative. ds dx is equal to, term at a time, 2x plus, and now we remember our chain rule. 2 times 20 minus x times the derivative of the inside. When we clean this up, go ahead and clean this up so that you can see that this is so. We get that ds dx is equal to 4x minus 20. And now to find critical points, we set equal to 0. Excuse me, 4x minus 40. There we go. Now to find critical points, we set equal to 0 and solve for x. And when we do, we get x equals 10 is the single critical point for our function. Having found the critical points, we are ready to evaluate s at each of its critical points plus its endpoints. Here are the endpoints. X can be no larger than 20, and it can be no smaller than 0. And here's the critical point right here. And we're going to plug our critical points and endpoints into the function s. Please remember that you are not plugging into s prime, but into s. So s of 0 would be equal to 0 squared plus 20 squared, which is 400. S of 20 would be 20 squared plus 0 squared, which is again 400. And s of 10 would be 10 squared plus 10 squared, which is equal to 200. So it's pretty clear that s of 10 is our min, and s of 0 and s of 200, excuse me, s of 20 are both our max. Having found the min and max, we need to come back and answer the question that was asked. Now, the question that was asked is, find the numbers. So we haven't quite done that yet. We have found values of x that give us max and min, but we haven't found both numbers. So to do that, we're going to go back to the fact that y is equal to 20 minus x, and we'll plug in our y values. When x is 0, y is 20. When x is 10, y is 10. And finally, when x is 20, y is 0. So that if the sum of the two numbers is as large as possible, then my two numbers are 0 and 20. Let me give myself just a little more room here. If the sum is as large as possible, the numbers are 0 and 20. Notice that the identity of the numbers as x and y doesn't really matter. X equals 0, y equals 20, x equals 20, y equals 0. Both of them give me the maximum sum of 400. If the sum is as small as possible, then my numbers are 10 and 10. I have answered the question. My justifying work consists of the critical point finding and the evaluation of the critical points and endpoints right here. And that's it. That's the whole process. It's a matter of translating from English into math, substituting if necessary, and then finding critical points and evaluating at critical points and endpoints. Let's do that for this one here so that we can see this process a little more efficiently. Here we are told that one number plus the square root of the other is as large as possible. And you remember that as large as possible is a code word for absolute maximum. So we're going to take one number, maybe x, plus the square root of the other, which would be y, and that sum is to be as large as possible. So I'm going to call that sum something, s. And since this is part B of the problem, I go back to the stem of the problem, and I notice that the sum of these two numbers is still 20. So x plus y is still 20. And the numbers are still non-negative, so I still have a domain of 0 to 20 for each. So that's the translation process. Now, in order to maximize or minimize the sum, I need to pull off a little bit of substitution. Question: should I substitute for x or substitute for y? If I look ahead just a little bit, if I substitute for x, I get a slightly simpler expression. So if I solve for x equals 20 minus 1, and plug into s, then I get s is equal to 20 minus y plus the square root of y. And that's just a little bit easier than the expression that I would have gotten if I had substituted for y. If I substitute for y, then I get s is equal to x plus root 20 minus x. All things being equal, I would rather take the derivative of this expression right here. And so I'm going to choose this one rather than the one over here on the right. Neither one is wrong. It's just that one is easier than the other. Okay? So now that we have our expression, we're ready to find critical points. We take the derivative, ds dy is equal to, derivative of 20 is 0, the derivative of negative y is negative 1, and the derivative of y to the 1/2 is 1 over 2 root y. We set that derivative equal to 0. And we're going to solve by clearing the fractions, by multiplying both sides by the denominator, root, the 2 root y. And when we do, we get the equation negative 2 root y plus 1 is equal to 0. Continuing our algebra by subtracting 1 from both sides, dividing both sides by 2, negative 2, and squaring both sides. We get y is equal to 1/2 squared, which is 1/4. And since y is equal to 1/4, as our sole critical point, we are now ready to compute the sum when y is equal to 0 at the endpoint, the sum when y is equal to 1/4 at the critical point, and the sum when y is equal to 20 at the other endpoint. Plugging back into our expression right here, you can see that s of 0 is going to equal 20 minus 0 plus the square root of 0. S of 1/4 is a little bit of a pain. 20 minus 1/4 plus the square root of 1/4 is the same as 20 minus 1/4 plus 1/2. Which is the same as 20 and 1/4, or perhaps we should call it 41 over 4. And then finally, s of 20 is equal to 20 minus 20 plus root 20, which is equal to the square root of 20. I did this wrong. This should be 81/4. Some of you at home were going, where is he getting that fraction from? Okay, so having evaluated these, we now need to figure out which one is the largest and which one is the smallest. And I think it's pretty clear that 20 is bigger than the square root of 20. And it is also pretty clear that 20 and 1/4 is bigger than 20. So our largest is going to be the max, s of 1/4, which is 20 and 1/4, or 20.25. And the smallest of these three is going to be the min, which is square root of 20. Now, again, we have to make sure we answer the question, so we can just go back and check. And we are supposed to, according to the stem of the problem, we are supposed to find the numbers. All right, well, I found y's, but I need x's also. So when y is equal to 20, then x is equal to 0. This gives us the smallest possible scenario. And when y is equal to 1/4, and x is equal to 20 minus 1/4, or 19.75, and that gives us as large as possible. So this gives you an overview of the process of optimization. Let's see how these problems work when we put them into geometric context. Page 226, number 15, we're told that two sides of a triangle have length A and B. Immediately, we should draw that triangle. Now, we don't know exactly what we want our triangle to look like, but that is okay. Here we have two sides, A and B, and the angle between them is theta. What value of theta will maximize the triangle's area? Okay, so we're looking, here's our key word, we're looking for an absolute max. We're looking for an absolute max of the area of the triangle. And they give us a hint in the stem of the problem. They give us a formula, area equals 1/2 A times B times the sine of the angle between. I'll take just a minute to show you why that formula is true, but you didn't need to know this for the problem. We know that the area of a triangle is 1/2 base times height. So if I draw myself a height and label it, and you see that we have a right triangle here, then height over A is equal to the sine of the angle between the two. That's opposite over hypotenuse. And therefore, height is equal to A times the sine of that angle. And since the area of any triangle is 1/2 base times height, if if I substitute for my height, a sine theta, then I get the indicated formula. So that's nice. But we didn't need to know that in order to solve this problem, because they give us the formula that we are trying to maximize. And if we have that formula, we're going to say thank you very much and go with it. Since we have the formula, we will find its critical points. dA d theta is equal to 1/2 times A times B times the cosine of the angle between. Please notice that A and B are fixed in this problem. We are given A and B as constants in this problem. Therefore, they are simply constant multiples. And the only variable that we have is the angle theta. And we set this angle, this expression equal to 0, which implies, therefore, that the cosine of our angle is equal to 0, because if A and B were 0, or B were 0, then we would have no triangle whatsoever. So it must be that cosine of theta is equal to 0. Now, cosine theta equals 0 has a lot of solutions. So we wonder about domain for this problem. Are there maximum and minimum values for theta? So we come back to our triangle, and we visualize. Let's get our right triangle out of here for just a second. And we visualize changing the angle, and we wonder what's the smallest angle we can possibly get. And we realize that the smallest angle that we can possibly get here is going to be basically when theta is equal to 0. Theta can't be 0, but it can come as close as it might to 0. In other words, our domain is theta greater than 0. Likewise, if I make theta as large as possible, we can see that I can take it all the way over to here until it's practically a straight line, or 180 degrees, or pi radians. So this is the domain for our problem. There's only one small thing that bothers us, and that is that this domain is not a closed and bounded domain. It's an open and bounded domain. So we wonder, can we include the endpoints here? Well, yes, we can include the endpoints for the purposes of solving the problem. And these two endpoints represent what we would call degenerate cases. If theta is actually 0, then I have no triangle anymore. I have a triangle with area 0. And if theta is actually pi radians, then I have no triangle anymore. I simply have a straight line, or a triangle with area 0. So we're going to include these endpoints here, but we understand that they correspond to degenerate cases. Now that we've established our domain, this means, therefore, that the cosine of theta is going to have solutions only on the domain 0 to pi, which means that theta can only have the value of pi over 2. If you were a little uncertain about the solution to that equation, then you should take a moment, pause the video, and practice drawing your unit circle so that you can see that the cosine of pi over 2 is in fact 0. So we're ready to evaluate critical points and endpoints. The area at theta equals 0 is 1/2 times AB times the sine of 0, which is 0. That's that degenerate case that we talked about. The area of pi is going to be 1/2 AB times the sine of pi, which is again 0. That's the degenerate case that we talked about. And the area of pi over 2 is going to be 1/2 times A times B times the cosine of pi over 2, and the cosine of, the sine of pi over 2, and cosine on the brain. 1/2 AB times the sine of pi over 2, and the sine of pi over 2 is 1. So that I get 1/2 AB. Well, pretty clearly this is our max. So now we want to do two things. First, we want to sketch our situation to see why it is reasonable. When theta is equal to pi over 2, we are looking at a right triangle. And it makes sense that the right triangle would have the largest area for a given value of A and B. So we're happy with our answer. Next, we want to make sure that we have answered the question. And the question is, what value of theta will maximize the area? So mathematical answer. Beta equals pi over 2 gives the largest area. This kind of answering the question according to the terms asked is good style. This is a good way of answering it. This kind of answer right here is poor style. It's not saying quite enough. It's giving the answer, but it's not acknowledging that you are answering the right question. Let's take a look at one final problem, and then we'll call it a day. On page 226, number 5, they have a figure. We'll go ahead and sketch out that figure. Like so, like so. And like so. Here, and there. That's good. And they mark a couple of things on the diagram. Then they have a rectangle inscribed inside of the triangle here. Okay, so the figure shows a rectangle inscribed in an isosceles right triangle whose hypotenuse is 2 units long. Now immediately we want to come back and see that the diagram is reflecting what the language says. So I have an isosceles right triangle, so immediately my mind says, well, where's the right angle? Aha, the right angle is right here. And why is it isosceles? Well, it's isosceles because these two sides are congruent to one another. And immediately my mind pings, this is a 45, 45, 90 right triangle, because that's what isosceles right triangles have to be. And they say whose hypotenuse is 2 units long, so I just check that. Yep, the hypotenuse stretches from here to here, that's 2 units long. Okay, good enough. Then they ask us to express the y-coordinate of P in terms of x. And so that sends us back to the diagram. They have point P right here. And they want us to express the y-coordinate in terms of x. And they give us a hint. Find the equation for this line right here. Okay. We're a little mystified as to exactly what they're asking. But we do know that if we find the line, that might give us a clue. So we're going to find the equation for the line, and of course to do that we need a slope and a point. And we have one point already, and that's the point right here. This point is the point 1, comma 0. And if only we had another point. Well, I see that this line hits the axis right there. So I think to myself, I wish I knew the y-coordinate for that point. Can I think of anything that would work? Well, this angle right here is 45. So this is a right angle, and this angle is 45. So this little triangle right here is also an isosceles right triangle, which means that the length of this side must be 1. And the coordinates of that point have to be 0, comma 1. I want you to think through that reasoning to see that it makes sense to you, that you would be able to do the same thing. The key point was to recognize that we had a 45-degree angle in the bottom right corner, which forces this blue triangle to be a 45, 45, 90 right triangle, and therefore the two legs have the same length. So now I have 2 points, and I can immediately see that the slope is -1, and it goes through the point 0, comma 1, so that I get y is equal to -x plus 1, or y equals 1 minus x. Well, in so doing, I have just gotten myself the y-coordinate of point P. Why is that? Well, because all of the points on this line satisfy y equals 1 minus x, or negative x plus 1. So P is on this line. And that means that the y-coordinate for P must be negative x plus 1. I'm going to write that as 1 minus x. Just can't help myself because these 2 points make it so obvious. When x is 1, y is 0. When x is 0, y is 1. Y is 1 minus x. Now we're supposed to express the area of the triangle. Now I believe the problem says rectangle. Let me fix that. Yes, it does indeed. There we go, in terms of x. Well, I know that the area of any rectangle is length times width. So I want to come back to this rectangle and carefully get the width and the height in terms of x. I can see that the width right here stretches from here to here. This coordinate is x. Therefore, this coordinate on this side has to be the opposite of x because the whole thing is symmetric. And that means that the length of this entire thing is 2x. Meanwhile, the height is the y-coordinate, which is 1 minus x. And now I'm ready to go. The area is length times width, which is equal to 2x times 1 minus x. And it might be helpful to simplify that as 2x minus 2x squared. This was the key point to unlocking this whole problem. So take some time to make sure that you could do the same thing when confronted with a problem like this. Talk yourself through it. And then finally, they ask us what is now a fairly easy question. What is the largest area? So immediately I recognize that we're looking for an absolute max that the rectangle can have, and what are its dimensions. Now, we need a domain so we can have endpoints. So we come back and ask, what is the absolute largest value that x can have? And of course, that is x equals 1. My rectangle can't go past the triangle. And what is the smallest value that x could have? Well, that would be x equals 0. If I make x equals 0, then my rectangle becomes this small, degenerate rectangle, which is basically a straight line. So we have, for our domain, x is between 0 and 1, and now we're ready for critical points. dA dx is equal to 2 minus 4x. Set that equal to 0 and get a single solution, and that is x equals 1/2. So now I compute the area at 0, the area at 1, and the area at 1/2. And when I compute the area at 0, pretty obviously I get 0. When I compute the area at 1/2, the area at 1, I get 2 times 1 minus 2 times 1 squared, which is also 0. And then finally, when I compute the area at 1/2, I get 2 times 1/2 minus 2 times 1/2 squared, which is 1 minus 1/2, or 1/2. Well, having found the absolute max, which is clearly the 1/2 right here, we now need to come back and answer the question. What is the largest area the rectangle can have? The largest area the rectangle can have is 1/2. And what are the dimensions of the rectangle? Well, the dimensions of the rectangle, as we saw before, are 2x for the length and 1 minus x for the height. And since x is 1/2 gives me the largest area, 2 times 1 1/2 is 1 for the length, and 1 minus 1/2 is 1/2 for the height. Well, I hope this gives you some insight as to how to optimize various functions.